Year 10. So if you remember last week we started talking about what happens to light whenever it starts travelling through different materials. So going from one type of material into another type of material. So the one that we talked about the most was going from like air into glass or perspex, which is what this wee block is here. Okay, so let me just remind you what actually happened. So what we found was that as our light travelled along and it hit this shiny surface, you can see there some of it did get reflected because it is a shiny surface. Some of it then actually changed direction whenever it went into the other block or the other material, so into this perspex block. And then if you look, it changes direction again whenever it comes back out the other side. Now, I'm going to ignore this wee one for now. It shouldn't really be here, okay? Now, the reason that it changes direction is because it is hitting here at an angle. If I aim my light so that it is hitting at 90 degrees, can you remember the name for what that's acting along? Or what the angle of incidence would be in this case? So remember, 90 degrees to the surface, we call that the normal. And because all angles are measured from the normal, this angle of incidence, the angle that the light is going in at, would be 0. And then it just keeps on travelling straight on. Now, what we can't actually see here is that the light has slowed down whenever it's gone into this glass block or this perspex block. It just looks like it's carrying on as normal, but it has actually slowed down. And have a wee think what we said that why that was last day. Can you remember? It's because the glass or the perspex is more dense than the air, and because of that it's harder for the light to get through. So that's why it slows down. It's literally harder to get through, so it takes longer to get through. So if you remember, we did a little practical last day, so let's just have a wee quick look at that. So here's the diagram that we had from our wee practical last week. We drew around our perspex block, and then we marked on the normal, and then we marked on a couple of different incident rays. The first one was an angle of incidence of 20, and that's this one here. Then what we did was we shone the light along here, and then we took some measurements to see what was actually happening to the light inside the block. So what we did was we marked on with these wee X's here where the light was leaving. Then that meant whenever we took this away, we were able to join that up, and we knew, right, well, the light went in at this point and it came out at this point, so it must have gone here in between. And then we took a bunch of measurements. So the letters for what the measure or what the angles were called were all in your notes. We'll have a wee look at that in a second. But we did that for this angle, and then we did it for an angle of incidence of 40, as well as an angle of incidence of 0. Okay, let's have a little look at the results and the answers that you have given me to the questions after that. So that was the work from last day that you had to show me. So these were the angles that we measured last day. Now let's just remind ourselves what all these letters stand for. So we found that with an angle of incidence of 20, so I've marked that on here in my black pen just to make it a wee bit clearer. So our angle of incidence of 20, the angle of refraction, R, we ended up measuring that wee angle there, we got 13. Angle X, which is actually the angle of incidence for this junction, is this wee angle here, so the angle between this ray of light inside the block and the normal. And then angle Y was this wee angle here of refraction on the other side. So the angle between the ray of light that was coming out and the normal, which was drawn on at the point that that ray of light was coming out at. So we measured these angles for our angle of incidence of 20, and then we did the same for the angle of incidence of 40. And then if you remember, there wasn't actually any measurements we needed to take here for this angle of incidence of 0. So let's go through these answers. So first of all, what do you notice about when the angle of incidence is 0 degrees? So what I have put here is that all the other angles are 0. The light didn't change direction at all. It just kept going in the same direction. Question 2, what do you notice about the angles I and Y in each case? So here's our angle I, here's our angle Y. If you look, they're exactly the same every time. So I've just put that in there. They are the same. Now let's add in an extra wee bit. So I want you to add this into yours. See this angle Y? We can actually call it the angle of emergence, which just means it's on its way out, it's emerging. Okay, so if you add that in for me there, and then add this in. So the angle of incidence, which was I, is equal to the angle of emergence, and the angle of emergence was the one that we called Y in that table. Okay, question 3, what do you notice about the angles R and X in each case? So here's R and here's X, and again they ended up being the same every time. So let's get that in. So I've just written they are the same for that one. Now if we remind ourselves what those letters actually were, so R was the angle of refraction in the glass, and then X was actually the angle of incidence for this next junction. I'm not going to bother writing that in though as a wee extra here. 4, what do you notice about the incident and emergent rays in each case? So if we look back at this, okay, here's our incident ray, and then here's our emergent ray, the matching one. In fact, you know what, I'm going to color code these. Okay, hopefully that'll make it a wee bit easier to see what I'm talking about. So the yellow line is the one that had the angle of incidence of 20. And if you look, they're both pointing in the same direction. So the incident ray and the emergent ray. Now obviously you didn't have this diagram unless you were drawing it along with me, but you can tell that from the angles in the table because the angle of incidence was the same as the angle of emergence. And then if you look here at the orange one, it was the one with the angle of incidence of 40. And if you look at the angle of that and the angle of that, they're both going in the exact same direction. Or what we could say is that they're parallel. Okay, so I'm going to write both of those in. So I would like you to add into yours that wee bit there about them being parallel. Okay, so they're going in the same direction, they are parallel. So question 5, why does the ray of light change direction on entering the glass block? So here's what I've put. The light slows down when it enters the glass block. Slowing down here is key. And then because it hits at an angle, it changes direction. Now, to be honest, this doesn't really answer the question properly. In fact, see this bit here, the light hitting at an angle and changing direction. That is what I really want us to understand today. So that's going to be the main focus of today's lesson, trying to get our heads around why that change in direction happens. Okay, let's look at number 6. Why does the ray of light change direction on leaving the glass block? Basically the same answer, except in this one, it's because it speeds up. So you can see I've written basically the same answer, but I've changed slows down to speeds up. So the light speeds up when it leaves the glass block. Because it hits the edge at an angle, it changes direction. So make sure that you are correcting any of those questions that you need to in yours, and then let's move on with today's stuff. So if you open your notes at page 75 for me, and then we're going to work through these notes and fill them in together. So when light hits a different substance at right angles, so that means right angles to the surface at 90 degrees, or we could say along the normal. So let's add that in. Along the normal, which remember means the angle of incidence, AOI for angle of incidence, is 0 degrees. The angle of incidence isn't 90, it's not, because remember all angles are measured from the normal. So the angle of incidence is 0 if the light's acting along the normal. So it's asking us to draw the diagram to show that here. I'm just going to remind you and show you here with the light and the glass block. So here's my glass block. I've got my light source over at the right hand side again, so I've moved away, I was over the left there. And I'm just going to aim this along the normal. So I'm shining my light there along the normal. And remember what we said, it sort of looks like nothing happens, but it does in fact slow down, I promise. So this is the diagram that we're going to draw in basically. Yeah, in that wee space. Okay, so let's get that done. Okay, so here's what I want you to draw. So this is our glass block, and then this is air on the outside, everywhere else that isn't inside that glass block. And same here. I've just drawn the same thing in 2 different directions, okay, so that we recognize it no matter what way the light is going. So it could be going across this way, could be going the opposite way. Same here, down or up. It could be going, if the whole thing was rotated, that would be fine. So if you draw that in for me there, please. Now just down the bottom here on page 75, it's asking us to draw another couple of diagrams, and again I'll show you it with the light first and then we'll draw it in. So let's see what it's asking. When a ray of light hits a denser substance, or glass block, at an angle to the normal, which remember the normal is an imaginary line at right angles to the substance, it slows down and its direction changes. When a ray of light hits a less dense substance, so that will be whenever it's going back into the air, it speeds up and its direction changes. Now the way that direction changes is important for the minute. We're just going to draw down what happens, then we're going to look at why that change in direction is the way that it is. Okay, so I've got my glass block again. I'm just going to aim my light here at an angle. Now, this wee line here that keeps showing up that's doing my head in is actually quite helpful, because see if this glass block wasn't there, then the light would just continue in a perfect straight line. But as soon as that glass block goes there, you can see the change in direction. Now, see the way this line here shows the way that the light would have been going? Do you see how the way that it now ends up going, because we can see this is where it's coming out, do you see how that is closer to the normal than the way that the light would have been going if the glass wasn't there? So the way that we word that is that we say it bends towards the normal. So whenever light goes from less dense air into more dense glass, the light bends towards the normal. By that I mean it's closer to the normal than it would have been if the glass wasn't there. Now, same again, but opposite on the way out. So whenever the light's travelling along here, if I just trace out, this would be going like this if it was still in glass, but the glass isn't there anymore, and now it's back out into air again. So now it's bent away from the normal. It's further away from the normal than it would have been if this change in substance hadn't happened. So let's get that drawn in. Okay, so back on page 75, before we start drawing the rays of light in, pause and get this drawn down. Okay, so because we're now hitting at an angle, I'm just going to draw my ray of light coming in here. So there's my ray of light coming in. Oh, forgot to label my glass block. So this is the glass, and this is the glass. All right. Now, you can use your ruler to help you with this, because remember what we were saying there. If the glass wasn't there, this would just continue in a straight line, but the glass is there, so it doesn't. It slows down and it bends towards the normal. So I'm just going to draw my line so that it's noticeably closer to the normal than it would have been if that glass wasn't there. Okay, so this is it, refracting, going into the glass. Then if I just draw on a little normal where it's met the other side, oops, okay, and then whenever it's going from the more dense to the less dense, it bends away from the normal. And do you remember from that practical, it should really be parallel to this wee angle, or this wee incident ray here. So further away from the normal than it would be, and try and make it parallel to that first one. Okay, and I'm going to summarize these rows just underneath. So get that one drawn in, and then we'll do the same here. It's the exact same thing, only it's vertical instead of horizontal. So if I draw my ray of light coming down in this way, then remember, if the glass wasn't there, it would just continue on like this, but the glass is there, so it bends towards the normal. So let's say it goes like that. Then we'll draw a wee normal where it's met the side of the glass here. Okay. And now if it was still in glass, it would continue this way, but it's not, it's gone into air. So it speeds up and it bends away from the normal. And again, I'm using my ruler to try and make that parallel to that one up there. Okay, so if you get, if you get those drawn in for me. Now, I'm trying to show here, or describe here I should say, what's happening at this boundary. So this is the light going from air to glass. So air is obviously less dense than glass, so we're going from less dense to more dense. The light's going to bend towards the normal. Okay, now we're going to run out of room if we try and then label for this one as well. So I'm going to use this diagram to label it the other way round. So pause, get this bit written in, and then we'll do the other way around. So at this boundary, the light is going from glass to air. Glass is more dense than air, so it's going from more dense to less dense, and it bends away from the normal. Okay, they're the key bits that we need to learn and to remember. The direction that the light goes whenever it's going from more dense to less dense, and also from less dense to more dense. Now, I said I was going to try and get you to understand why that change in direction happens the way that it does. So we're going to try and do that now. Now, every time we're drawing our light diagrams here, we draw it as if it's just one wee tiny beam of light, the type of beam of light that we get from our light box here. But in reality, it's not. It's actually a much wider ray of light that will be going in. So I'm going to try and use two colours here to show you what's happening. So I'm going to use green and pink. So my pink and green pens are just representing this ray of light here, and they're going in and they're hitting this block of glass. Again, I forgot to label it, at an angle. So if I move these in, let's see what happens. Which side of the light hits first? The pink, right? So the side of the light that's closest really to the denser material is going to hit the block first. And you remember, whenever the light goes from less dense to more dense, it is harder for it to get through. So that means that this side of the light is going to slow down first. This one's living its best life over here in air. It's flying along, but this side has started to slow down. So because it's slowing down and the green side is still going on, then it ends up changing direction. And it's only once that green side has joined up really, or like caught up and it's in the glass as well, now they're both travelling at the same speed, so they go in a straight line. And then look, the pink one here is hitting this boundary over to air again first, so it's going to speed up, whereas the green's still going really slow, and we end up with this little change in direction happening. Okay, so that's one way I wanted to try and show you and help you understand why that change in direction happens, because this is really tricky to get your head around. So if you try and model this for yourself as well, so you've got two different coloured pens, travel along, see which one hits first. Pink one's hitting first, so it's going to slow down first, and it ends up making the whole thing change direction. Now there's a wee bit in your notes about this, which is also a really good way of getting your head around it. So if you turn to page 76 now in your notes, why does the light change direction? There's a wee video clip that I would normally show in school for this. I will try and find it on YouTube and link it for you to watch, but if I can't find it, then try and understand what I'm talking about here. So if we imagine a truck driving from a road onto mud, when the first wheel of the truck hits the mud, it's going to slow down. The other wheels keep on going at the original speed because they're still on the normal ground, and this pushes the truck in the other direction. So that's what this wee diagram's showing us. It's the same idea as with the two different coloured pens. So if our truck's travelling along, this wee wheel here is going to hit first and slow down, and because this side is all still going really, really fast, it's going to end up changing direction, and then it'll go here. And then the opposite happens then on its way out. This side is going to speed up first, and then because these ones are still going slow, it ends up rotating around the other way. So say I'll try and show you. It's just honestly a wee 30-second clip, and it is the thing that makes this click for most people. So I will try and find that for you. So this is similar to what happens when light travels from air to water or glass, because water and glass are both denser than air. Or when water waves go from deep to shallow. That's a wee weird one if you do GCSE physics. That's very, very important. For now, if we can just get you with the light going from less dense to more dense and understanding that, we will be flying. Okay, so as the light slows down when travelling into glass, the ray changes direction. As it leaves and speeds up again, it changes direction for a second time. Now if you turn over to 77 for me please. This wee diagram hasn't photocopied very well, so I'm going to ask you to fix it with me here. Okay, so this is actually a wee glass block, but the outside of it hasn't really photocopied. So if you draw this in the same as me please, then it'll make it a wee bit more obvious what's going on. So this is the diagram that we have been drawing, but we haven't really labelled, we labelled them all last week. I was going to say we haven't labelled all the angles and things. We labelled them last week. So this is our ray entering. Remember, we call that the incident ray. Okay. And then whenever it has changed direction going into the glass, then it's the refracted ray. Okay. This here is the emergent ray, or the ray emerging. So if this is the incident ray and this is the normal, then this here must be the angle of incidence. And then this here's the refracted ray, this one, and that's the normal. So this is the angle of refraction. Oops. Okay. Now down here we do have a separate situation where this would now be an angle of incidence and an angle of refraction, but it's going to get a bit messy if we try and label it on. So if we just go from the air to the glass and label those on. Now, this here is a good diagram, okay, and this can be really, really tricky to get our head around. So because of that, we're going to do a little bit of extra notes here, okay. So see the way there's all this empty space down at the bottom of page 77? We're going to learn a little bit about waves here. So, if I was to ask you to sketch a wave, you probably would draw this shape, okay. So a wee wave like this, right. Now, I'm going to just mark on like the midpoint here with a dashed line. And what this is just the pattern that the particles take whenever there's energy traveling along. So this would be a light wave, and the particles would just be vibrating about an equilibrium position, okay, so which I've drawn on here with the dashed line. So the particles vibrate up and down, and they do so in such a way that it creates this shape here. Now, just let's label a few wee parts of this. So all these top bits are called peaks, and all the very lowest point are called troughs, or sometimes they can be called oh no, that's a lie, hold on, sorry, the peaks can also be called crests. Okay, I very rarely use that word crest, which is probably why I was about to label it the wrong way, but peaks and troughs. Now, the height of the wave, we call that the amplitude. Okay, so I'm going to mark it on from here to here. I could have marked it on lots of different places. I could have marked it on here or here, but it's just the maximum distance or displacement that the particle goes from the equilibrium position. So this is the amplitude. Now, to be honest, year 10, for this topic, what I'm doing here is a little bit too in depth, but our next topic is sound, and all this comes up again in it. So well, it's a good idea to get ourselves a wee bit ahead. Now, one complete wave would be like from here to here. Do you see how once we've followed that shape, we're just repeating the same shape over and over again? So one complete wave, I'm going to do it here because I've got a wee bit more room there, would be from there to there. And we call that distance the wavelength. Now, you might be like, why on earth is she telling us all this? Well, if you try and imagine this like water waves, okay, and if you imagine you're looking down on them, then you're probably going to see all these peaks, and they're going to look like straight lines. Well, that's what this diagram here is showing. These wee lines here are called wave fronts, right? And if you, and if you imagine you're looking down on this, it's just showing you all the peaks of the wave. Okay, and what this is showing you is that the light slows down whenever it goes from deep water or into shallow water, or if it's going from, if it's light going from less dense to more dense. And again, do you remember last week I talked about how, like, if you're walking in the corridors in school and they're empty, there's loads of, well, say there's a few people in it, there's loads of space between you and the other people. But say it's like time to go to assembly, or it's the end of school, or the start of break or something, and there's loads and loads of people all trying to go the same direction, you all get really squashed up. Well, that's what happens here. The wave fronts, or these peaks, all get really, really squashed up, and that happens whenever they're going really slow. Okay, so I just wanted to try and explain what this diagram means, because it is tricky. Okay, Now, one last little thing. Do you remember? Oh, wait, before I show you that, this here is also really good at showing why it changes direction. Do you see how this end of the wavefront hits the denser or the shallow water much earlier, couldn't get that word there, earlier than this side? So it's slowed down, these all slow down, this is all still really fast, and that's why it changes direction. Now just one last thing I do want us to draw down. Do you remember we said whenever we had our glass block and we had our light shining along the normal, that it just looked as if it didn't slow down at all, but we know that it does because it's going into a more dense material? Well, if we were to draw our light, say it's going down this way, okay? So far, that's all we've drawn there. We've just drawn our light and we've said, yeah, it travels, happy days, travels on through. However, if we were to add in the wavefronts, it would show us that it had slowed down. So I'm going to draw them just with green here, okay? So they're always drawn perpendicular to our wave. So let's say that's them there. Whenever they go into the denser material, they all get really squashed up, like the people in the corridor. Whenever there's loads of people trying to go the same direction and everyone's going much slower, we all get really squashed up. Same idea with the light. So if you draw this down with me, please. Oh, I'm not doing a good job of keeping all my lines the same length. What I'm concentrating on here, year 10, is keeping this distance between these lines consistent. Not doing too bad a job at that. I'm doing a terrible job at keeping them all the same length. Okay. Now, I kind of regret drawing that so big now. Then whenever they're back out in the air again, they're going to be the same distance apart as they were at the start here. Right there? Yeah. Okay. So let's label that and then that'll be us. So, less dense, traveling faster. This is the light whenever it's in the more dense material. Traveling slower. The wave fronts get bunched up, just like people in the corridor when there's loads of them. And then here we're back out into the less dense. So it's going faster again and they can spread out. Oh dear. Okay. So here's what you need to do. You need to make sure you have written down absolutely everything that I have. If you haven't, go back and write it in now and then send me pictures of your filled in notes, and that way I know that you've tried your best to understand this, okay? Because it is tricky stuff. Now this is only half an hour, so do take your time on going over and trying to make sure you understand what is going on there with the change in direction. So that bit with the two different coloured pens, or with the wee truck going into the mud, I think they're the best way at trying to get your head around what's going on. Okay, that's me. I'll see you next week. Bye.